So you have passed the wave types quiz, and now you're moving on to the wave measurements quiz. And so you got to think like a teacher here. What might you want to measure about a wave? So what would you want to know about a wave? One of the things is wavelength, and that's pretty easy to measure if you have a graphic like this. So this graphic shows us a transverse wave. This graphic up here shows us a compressional wave. Let's start with the transverse wave. If we want to know the wavelength, all we do is we pick a spot on the wave, like maybe this spot, and then we trace it out until it's doing the exact same thing again. So here I'm at the top of a crest. I had just come up and I'm about to come down. So if I trace through this, from there to there, that is one wavelength, this distance. Instead of writing the word wavelength, we often use the Greek symbol lambda. So how far is this? Well, this looks to me like it goes from 5 down to 1, so that wavelength is 4. What are the units here? It doesn't say. I mean, if the graph says, it might be meters, it might be micrometers, who knows what it is, but this wavelength is 4. And up here in this compressional wave, one wavelength is from one compression to the next compression. So if this had some kind of a scale on the bottom, we would just use that scale, and the wavelength is from one compression to the next. So if we go back down here to the transverse wave, did I have to pick this spot? No, I could have picked this spot right here. And here I'm at the 0 line and I'm going up. When does it do that again? Some kids pick right here. That's actually not true. Here you're at the 0 line, the equilibrium line going down. So that's not right. This is the next spot that's the same because you're at the 0 line going up again. So how far is it from here to here? It's 4. And we already knew that, but if you want to do it the easiest way possible, you might as well start at 0. Going back up here to the compressional wave, did I have to pick from compression to compression? No, I could have picked from the middle of this rarefaction to this rarefaction. And wherever I stole this graphic from, sometimes you'll see a compressional wave drawn as a transverse wave. I kind of don't like that because it misleads kids. They think that they're the same thing, but whoever made this image, they put this transverse wave up here to simulate this compressional wave. Why would they do that? Because sound involves changing pressure levels. So if you have a high pressure sound wave, the pressure goes up and then the pressure goes down where there's a rarefaction. So you can actually take a sound wave that is, all these little air particles, and you can draw it as a transverse wave if you want to. But I don't want to go too far off my path here. Okay, so what's next on my list? How to measure amplitude. Amplitude is also pretty easy. Amplitude is the difference from the equilibrium line, or 0, up to the max here. So it looks to me like, what's this, 1, 2, 3, 4, so this is 2.2 each time, so this looks like it's 2.4. What are the units? I don't know, I've deleted most of that. The units here, who knows, it might be meters or something else, but amplitude is the height of a wave. Now, it doesn't have to be in distance. I mean, if you're shaking a rope back and forth, but if you're talking about like this sound wave up here, where I was talking about the pressure going higher and lower, this might be measured in air pressure, or it could even be in decibels or something like that. But for the purposes of my quiz, the amplitude is just the distance from the 0 line, either up to the top of a crest, or from the 0 line down to the bottom of a trough. And so measuring amplitude is not too hard on this quiz. But measuring frequency is a little bit tougher, because to measure frequency, we've got to have some kind of a scale on the bottom here. So for this graph, I'm just going to say, I don't remember what it was originally, but I'm going to say that these are seconds. Okay, so 1, 2, 3, 4, 5, 6 seconds. To measure frequency, frequency is the number of waves per second. So all we need to do here is count waves and then divide by seconds. Gosh, I said it was hard, but that's pretty easy, isn't it? So I'm going to trace out one wave. So I've got one wave is right there. So that's one wave in 4 seconds. So that means my frequency is 1 over 4. That is 0.25, and seconds is on the bottom, so it's per second. Or a lot of people will write 0.25 hertz. Hertz is the same thing as per second. So that's how you measure frequency. Now, if I had wanted to, I could have traced, let me pick a different color here. I could have traced out, here's one wave, and then here's a half of a wave. So that's 1.5 waves in 6 seconds. And if I do 1.5 divided by 6, yeah, I get the same answer again. So it doesn't really matter how many wave chunks you pick, as long as you have waves per second. That'll give you the frequency. Now, period. Once you have frequency, period is a breeze. Period is the time it takes for one wave, and that is 1 divided by the frequency. So, so we have 1 divided by our frequency was excuse me, 0.25 per second. I'm just going to leave the units off here. 1 divided by 0.25, 1 divided by a quarter is 4. So you should be thinking, well, hold on now. I didn't need to do that math because period is the time. Ooh, bad color choice. Period is the time for one wave. So if we're looking at the time of one wave, why don't we just trace out one wave and look at the time? Right here, yeah, it was 4 seconds. So the period was 4. We could just measure it directly from the graph instead of doing the math if we wanted to. So trying to finish up before 7 minutes, we'll see if that happens. How do you measure the energy of a wave? Well, I'm not sure I can go into that in this class very well, but I can talk about two things. The energy of a wave is affected by a couple of things. It's affected by the amplitude and by the frequency. Because think about this. If you're out on a boat and there's a wave in the water like this big, and you're like, yeah, whatever, that's not too scary. But if you're out on the boat and then there's a wave coming at you like this, you're like, uh-oh, that's a problem. So this high wave, this really tall wave, this high amplitude wave has a high energy. So that's one thing that can influence the energy of a wave. Okay, so I didn't make 7 minutes, sorry. Think about this. Let's say you're out on a boat and it's smooth water, but then there's a wave coming at you, and then a little ways away there's another wave coming at you like this really long wavelength. So the wavelength is pretty long here. Yeah, you're like, I can deal with that. That's not too big of a deal. But what if the waves coming at you are not long waves, but there's a whole bunch of short waves coming at you? This is a horrible drawing, but look at all these waves that are going to hit you, all these crests. So that's a lot more energy. So if you have more waves, in other words, a higher frequency or a shorter wavelength, you've got more energy. And if you've got a higher amplitude, you've got more energy. So if we're talking about these sound waves up here, if we could really pack these compressions together a lot, we would have a very big pressure difference. So that would be more amplitude. If you understand that, then you're going to be good to go on my wave measurements quiz.